Okay, it's me, Aaron Stump. I'm here with Andrew Marmaduke, doctoral student at University of Iowa, and we are talking a little bit about Tableau and their connection to optimal beta reduction. And so the first thing we'll talk about are what are tableaux. So actually there's some, you can be pretty picky about this. Tableau, of course, is a French word, and but it's a loan word now in English, so we can speak about tableaus with an S instead of tableau with an X at the end, as it would be in French. Anyway, that's just a tiny quibble. So these were introduced by Smolian. I actually noticed, by good luck, I actually have the Smolian book on first order logic on my shelf. I've never read it, but now I'm keen to read. And sure enough, there's his proof notation is tableau. So this idea of tableau is from Smolian, Raymond Smolian. And the basic idea is, so what the connection with optimal beta reduction is that we, oops, and here I had a connection problem, just a second. Tableau are a particular kind of graphical format for proofs. Now, they're not graphically close enough to, like say sharing graphs that we would have in optimal beta reduction, but we can start to go from Tableau to those graphs with some intriguing benefits. So the kind of the starting point is that this is some kind of graphical notation for proofs. And you say, oh, if you're familiar with some of the background of optimal beta reduction, you're thinking, oh, you mean they're like proof nets. Well, I think these came way before proof nets, so I think you could say proof nets are like these. And I'm definitely not an expert on proof nets and becoming more knowledgeable about Tableau, but Tableau are a very pretty simple idea, and originally I'm gathering, but I haven't again checked out those sources. Originally, we're talking about for classical logic, but they're used for they're actually used in automated theorem proving, and my impression is that they've gotten some good success for non-classical logics. There's a whole conference called Tableau with an X. So now maybe I will be seeing what they're working on these days in the Tableau conference. I did do a little bit of checking, and I can assure you that they're not working on what I'm about to tell you. They're not. This is a new observation as far as I can see. And we're going to use it for, we want them for intuitionistic logic. But maybe the best thing to do is just start with the classical version. And it's a very simple idea. So, okay, so let's talk about what are tableaus for, let's say, just for propositional classical logic. The idea is that we're going to grow a tree from actually now I'm actually now become very familiar with how to do this for intuitionistic logic, and I hope I'm going to do it right for classical logic. So we're going to grow a tree from let's see, so tree labeled by signed formulas. And so a signed formula means like plus, I think T and F are often used for true and false, plus F and minus F. Intuitively this is saying F is true, and this one is saying F is false. And so what you do is to prove, say you're trying to prove some formula f, you start out your tableau, you start your tableau with minus f. With saying f is false. And what you're going to do, this is basically a method of proof by contradiction. You're going to say, let's start out assuming f is false, and we're going to deduce a bunch of consequences to that until we can see that we derive contradictions under all sort of possible situations. And you then extend your tableau in one of several ways, depending on your form of your formula f. So so branch extension. So in other words, we started out with a trivial branch that just has minus f sitting there, and now we're going to extend so we're going to extend this branch with some branch extension rules. Okay, and so so the rules say actually, let me just try to write something and explain a little more how you're supposed to use them. So let's say you had f1 and f2 positively. Okay, then you can extend your tableau. So that means you're saying we're assuming f1 and f2 are true. That means you can conclude from that f1 is true and that f2 is true. And so the idea with a tableau, simple tableau branch extension rule like this is saying if this formula, sign formula, occurs on the branch you're on current branch, you can add, extend the branch with these other guys. These guys, f1 being plus f1 and plus f2. Okay. So for example, like let's say so that was a positive one. We need some negative ones since we're going to start out trying to prove some example formula. Well, let's just say what would be the for symmetry and sort of duality, if we said what's the negative or rule. So if we had negative f1 or f2, well, again, by De Morgan duality, this is pretty much the same. It says if you know this disjunction is false, then you know that each disjunct must be false. So that's another one of these. Let's see. Now somewhere, and here I think I will try to see if Smolian's book, so I can just barely reach on my tether here. Actually, which I have yet, this is my first flipping through this, but I'm hoping I can understand what I will see here in a short time. Let's see. Yeah, okay, so then we switch polarities when we get to negation. It certainly makes sense. So if you say, if I know that not f is true, then I can add to my branch that f is false. Right? I mean, that makes total sense. And similarly, if I knew that not f is false, then I could say I know f is true. All right, so you can see once we have negation there, then now we see how we could switch the signs on these sign formulas, and that almost gives us. I mean, since and negation, let's just include a few more of these sort of things. And in particular, it's good to have some of the branching rules. So these talk about just extending one branch, but you do have to split your branches. This is an intriguing part of the idea of tableau due to Smolian. So if you know that f1 or f2 is true, well, then of course you don't know which one it is, so you have to fork your branch. And so this notation, what I just wrote here, is saying at the end of your branch that anywhere on this branch, it doesn't have to be right at the leaf of the branch. It could be anywhere on there. You've got this disjunction. Now at the end of that branch, you now fork and create a split in your branch. Okay, and so these are. This is now. Oh, and dually, I could show. If the disjunction is false, then dually it's the same deal. One of the disjuncts is false, but since you don't know which one, you do have to split your tableau. So we could try to do a. Now this isn't quite the end of the story with what's a tableau proof, but we can finish the story by just doing some pretty simple argument. Like let's say, I don't know. How about? Well, I guess if we really wanted to be short and pretty sweet, we could just say P or not P. Let's say we're going to try to prove this with a tableau. So what we do, so prove this. Well, what we said you're supposed to do is you start out with your tableau where you're more or less assuming that's false. So you put a minus there. And if a disjunction is false, let's see, somewhere up here we had one of these that says, yeah, that just means both disjuncts are false. So this is our branch extension rule. We have this one that's in the screen there. So if we come down here, say, all right, so that means that P is false and not P is false. Now we have, well, this example actually, to make this a tiny bit more interesting, not by a huge amount, let's just say it was not P or P, just so we can kind of see that branch extension doesn't have to be from the formula currently at the end of the branch. So this would say not P, not P is false and P is false. Now we're gonna do a branch extension with that not P. So this next step I'm about to take, comes from this guy. But there's nothing in the tableau notation that records that it came from there. It's just somewhere on the branch I have this not P, and that lets me add now to the end of my branch that P is true. And now we come to the last part of what the tableau proof is. You start with your assumption that your goal formula is false. You apply these branch extension rules, possibly having to split. This example didn't show splitting, of course. But we could try to come up with one where you do have to do that. And finally, though, you get to a point where, look at this branch. Hey, it says P is true and P is false. That's great. That's an obvious contradiction. And so then one says you close the branch. So you close the branch I'd have to see what Smolen says the official definition is of what does it mean to close a branch. Let's see. Well, okay, I'd have to look it up a little bit more. But intuitively, you either are observing or maybe actually drawing a connection of some special kind between the positive and the negative guy, and now this branch is closed. And if you can close all your branches, you've shown all those possibilities you've deduced are contradictory, and so your original goal formula is true. So here we are, indicating that the branch is closed. And again, it would certainly be enough as far as giving a definition of what a tableau proof is to simply say, on every branch you must find positive f and negative f for some f on one branch and possibly a different f on another branch of your tableau. So that's the basic idea of tableau. I can ask Andrew if any questions or thoughts or reactions to that.
I'm curious how these, because it seems like the history of the branch is like recording the context. And if you're thinking about this in like a secret this is maybe not a bad thing to do, but it seems like it's recording the context of things you've already shown, and so you can always use them.
Yes.
But now that makes me wonder if you move to like an intuitionistic setting, you have to apply some. It seems like you would have to apply some restriction to that.
You're right. Yes. So the question is, how do you? This seems like this would be too permissive for intuitionistic logic, and it is. It is. But there's a simple fix for that. It's a simple fix that uses basically the exact same machinery, just a little twist to it, and it's okay for intuitionistic logic. But you're absolutely right that just as we have here, this is too. We just proved P or not P, so
Yeah.
we know we're definitely not intuitionistic here. So let's see, but so the path I'm taking to optimal beta reduction is, so from here we have some kind of graphical notation for proofs, but it doesn't, this is hardly, looks like we have lambda calculus somehow hiding here. This is doesn't look like that at all. So to get to a form of sharing graph, just to kind of give a preview for motivation, sharing graph for lambda terms, what are going to be kind of the steps? Well, first we need to do what you just said, which is one, we need to switch to intuitionistic logic. Why do we need to do that? Well, because under the Curry-Howard isomorphism, lambda calculus is corresponding to, well, at least type lambda calculus corresponding to intuitionistic logic. If we try to do somehow Curry-Howard isomorphism for these classical tableaux, well, perhaps we'd get some intriguing form of computational classical type theory, but we don't. That's just as unknown, but even more unknown because I haven't thought about that at all, as this other version, which is what we actually kind of want. So we first need to switch to intuitionistic logic. Then we need to switch from this idea of branch extension, which is really nice and elegant and quite cool. But it's not, the problem with that is we don't record in the tableau where this, I drew this red dotted edge there in our example to kind of indicate, oh look, we did this branch extension because of this particular node way up there. But that's not actually, that edge isn't part of the tableau. But if you're going to have some kind of term notation or some kind of notation for a lambda term, we sort of need to know, I think, we need a more explicit connection between the consequence on some branch and where it originates. And so we need to switch from branch extension to a graph notation. I don't know. The tableau notation is a graph notation, but a graph notation where consequences are connected to their origins. In the graph to the origins. And once we do that, we will see this will sort of force you to add duplicators, to add some sharing nodes. Because, that's another thing about the tableau is that nothing says you can't apply a branch extension rule multiple times with the same origin node. Here I did this branch this way, but I could have just as well said, oh, I've got this not P, and you know what? I want to just do it again. I could have said, yeah, let's add P again here, which would be totally silly, and in fact isn't needed. I think there's a theorem that says that for propositional logic anyway, you never need to analyze, that is to apply a branch extension rule to a node more than once. You just apply it once and that's all you need. For first order logic with quantifiers, you may need to use it, a quantified assumption, several times at different instantiations, and so you may need to use it multiply. But for just propositional logic, somewhere in one of these sources I've read about this, I think I was seeing that there was some kind of theorem that said that for propositional logic, no. You just apply branch extension rule once to node, and that's all you need to do. You're just kind of trying to break down information down to these contradictions between atoms. But there's nothing that says that you can't do this, kind of unnecessarily apply a rule twice. And if you do that, then now, imagine you've switched to some kind of graphical notation where you connect a consequence like positive p down here to its origin. Well, now I can have multiple connections, and so unless I want to just say that my graph kind of has sort of multi-arity nodes, I'm going to be sort of generally dealing with having a graph that has some kind of sharing node. And that starts to sound like, oh yeah, that's the kind of stuff we have in optimal beta reduction. Okay, well, that's the intriguing teaser for more of this. So I've carried out this program, at least in my head, and even some on paper, to go from these two steps. And even, there's a third step, which is we need to introduce cuts. This is a cut-free formalism. And the fourth step is we need to define reduction on cuts. Define a cut reduction that that respects beta equivalence, beta 8 equivalence, or whatever, at least beta equivalence. We'll see that basically when you switch into intuitionistic logic, certain kinds of information flowing one way or another, as you were trying to simplify a cut, there'd be really nothing to prevent you from having information flow around in a way that's permitted by the logical view, but doesn't make sense from a beta reduction viewpoint. Sorry, this is a little bit too unexplained at the moment to really make a ton of sense, but it basically comes down to we need to solve the problem of duplicating lambdas, which is basically the central problem of optimal beta reduction. But the tools that we'll have introduced at that point seem to be giving us a new way to do it, which is pretty cool. All right, so I'm going to sign off now because I have to go to a faculty meeting, which is not something I'm looking forward to doing.